is Wied Pakusa, who's going to be talking about some other aspects of this related to groups and rings instead of fields.
Thank you very much. And yeah, more on linear algebra. Again, I want to look at solving linear equation systems, but now not only over fields, but over groups and rings. And throughout my talk, whenever I say group, then I really mean finite abelian group. And if I say ring, then I mean finite commutative ring.
I can turn on the mic.
Oh. Now it's on. So this, as you see, is joint work with Anu Stavar, Jacques Holm, and Erik Kopczynski, who are here. So what is the motivation for studying linear algebra from the viewpoint of definability? We have this very strong and robust logic, fixed point logic with counting, which is quite well studied, but which cannot express very simple problems from linear algebra. And specifically, it cannot express the class of solvable linear equation systems over any finite fixed abelian group. And so we saw this rank logic would strictly extend this logic, and by now we don't know any example which is not expressible in this logic. But matrix rank is a very nice numerical invariant. It characterizes matrices up to equivalence and gives you much information about the underlying vector space. And you can solve linear equation systems. You saw this criterion here. So such a linear equation system is solvable if and only if the rank of the coefficient matrix is the same as the rank of the coefficient matrix plus the solution vector. Why is this true? Recall, if you take a set of columns from the matrix A, so C1 up to CR, and these are maximally linear independent set, and then you add the solution vector B, then this becomes, if this criterion is satisfied, linearly dependent. This means you find some coefficients A1 up to AR and another coefficient A such that you can express the zero vector. And then you obtain a solution only by dividing by minus A. Then you have a solution. So, but dividing by minus A is a problem in a more general thing. Maybe slideshow is not the best way for this kind of overlays. However, so if you have rings, for example, then you cannot divide by every element. And if you have groups, then you don't have multiplication, so division is not defined. And so then you might say, okay, so then take something, a rank concept over rings, which is appropriate. But the problem is that over rings, you have, first of all, many notions for ranks. So for example, you could take the same definition with linear dependence, or there is this notion of McCoy rank, or this notion of inner rank, and so on. And they all are not equivalent. They are all equivalent over fields, but not over rings. And more strikingly, we don't know whether we can compute them in polynomial time. Maybe they are not computable in polynomial time. There are no results on this. And even if they are, then this, at least this characterization for solving linear equation system fails. So the question is matrix rank in general, so over these general domains, really the correct concept for solving linear equation systems? And we don't know by now whether this problem is actually in fixed point logic with rank, because for fields we can express solvability, but over groups, So this motivates to study these problems, and at least two very natural questions come into mind. Now, first of all, you have these solvability problems, and we saw already, they are very dependent on the underlying domain, so groups, rings, fields, and so on. So you might ask, what is a very natural, complete domain, or very nice complete domain, so that all of the problems reduce to this. So you only have to consider this domain, because there are many rings and many fields and many groups and so on. And one result I want to present you today, which is in answering a little bit this question, is if you have so-called k-ideal rings, I will explain later what they are, which are a very big class of rings already, then you can reduce in fixed point logic solvability problems to very basic groups, namely groups of prime power order, cyclic groups. And these are the most basic abelian groups which exist. So we can go from complicated rings to very easy groups, at least. And another question you might ask, okay, so we had these rank operators, but you could also, of course, say, then put these solvability problems to the logic. And this is what we did. So we started with first order logic, and again we now fixed some finite field because this is a little bit more well behaved. And for this kind of logic we established a very strong normal form. So we showed that every formula is equivalent to a formula where you only need one application of a solvability quantifier. So these two theorems I want to show you, and at the end also come to some open questions and further things. So okay, let's look at this first question of interdefinability. So we want to reduce solvability problems over these rings to cyclic groups. So let's first look what are these rings. So K-generated ideal ring means that whenever you take an ideal in the ring, which is a proper ideal, so not the ring itself, otherwise it would be trivial, then this ideal is generated by K elements. So you can think of the bad part of the ring is generated by K elements. And then, yeah, cyclic groups are clear. These are such easy groups. Yeah? So in order to achieve this reduction, we have to add two intermediate points here. This point is solvability over ordered rings. This means you have an ordering on the ring, not on the linear equation system, but only on the ring. And here, this is a very important notion from ring theory, which is local. What does local mean? A ring is local for finite commutative rings if and only if we have that the set of non-units forms an ideal. This means whenever I have a non-unit and another non-unit and I add them, I get another non-unit. And your favorite rings, the integers modulo m, they are local if and only if m is a prime power. And you all know the Chinese remainder theorem. Every such ring, the integers modulo m, decomposes into such local rings, namely rings of prime power order. And with this in mind, you may believe, if you don't know this notion, that this is the generalization of this Chinese remainder theorem idea to arbitrary rings. And in fact, it is true that every finite commutative ring can be written as a unique sum of local rings. And moreover, these local rings, you can define them from the ring itself only by multiplying some elements to the ring. So they are principal ideals in the ring. And what we proved is that the set of elements you need to obtain these summands is definable in first order logic. And not only that, but also that you can, in first order logic, express a mapping from the ring into each of these local summands. So this means in general, whenever you deal with problems from linear algebra over rings, you only need to consider them over. Yeah, so we have to be precise here. So this is, I always talk about finite commutative rings. And every such ring is a unique sum of local rings. Yeah? No, only finite commutative rings, yeah. Yeah, for infinite rings and non-commutative rings, this is not true. Okay. Oh, yeah, it sounds good. I've read something about. Okay, so now we have reduced to local rings, and now we want to order local rings. So recall we have this idea, which is a set of all non-units, and so this is a maximal ideal. So if I take now the ring and consider the quotient ring, then I obtain a finite field. And now let's take all the units in the ring, whose order is somehow compatible with the order of this field, and this I call gamma r, and this is known as Teichmüller coordinate set. The nice thing about this set is that it gives you a set of representatives for this finite field that you find in the ring. And this bijection here is very easy, so it's a canonical bijection, and so it's definable. So what we have is a set of units, which is a set of representatives for this finite field. And now, again, something you have to recall from your basic algebra course, every finite field has a cyclic group, cyclic multiplicative group. So you can take a generator of this group, and then you obtain an ordering on the field. And then via this bijection, you also have an ordering, of course, of this thing, which is nothing else but a set of representatives for this field. So this is the first main ingredient, and the other main ingredient is that we proved that now what you can do is for every ring element, you can define a unique expression which looks like this, So it's a polynomial expression, but the variables are substituted by somehow generators for these maximal ideal M. And all the coefficients are now from gamma R. So this expression is not unique normally, but you can define a unique one. And if you believe that this is possible for every ring element, then of course you can now order the ring elements by only taking the lexicographical ordering that you obtain by this expression. So these rings can be ordered with fixing some elements. So why do we need ordered rings now to come to these cyclic groups? So if you proceed in the natural way, take the additive group of the ring, and then you know this R is a direct sum of cyclic groups and so on. But now, the same as above, we want to fix a set of generators. And this turns out to be not possible without having an ordering, because there are automorphisms, and so you would not be able to define such a set. So here we really crucially make use of the order to define such a set of representatives, and then modulo some technical work, you can then decompose the system again into systems over these cyclic components here. So we have thus a reduction from very complicated rings to very easy groups in fixed probability. Of course, an open question I can now already say, of course you would like to have here every ring, but maybe this is not possible. Okay, so this was somehow related to this first question, and the other question is now let's consider these solvability problems as logical operators. So we can formalize them somehow as generalized quantifiers. You could say, they get as input a coefficient matrix and a solution vector and maybe even a finite ring. And then you would obtain extensions of first order logic plus these solvability quantifiers. And now if we again restrict ourselves to fixed finite fields, like in the case of the rank logics you saw, then we write a little f here and obtain for every finite field such an extension plus solvability operators over finite fields. So, and for this logic, we can show that we have a very strong normal form. So every formula in this logic is equivalent to a formula of this kind. We have one application of a solvability quantifier, and then everything else is quantifier free. And the solution vector is even specified with only with the formula true. So you can again think of all the matrices only have zeros and ones. This is sufficient. So to prove this theorem, if you do this, then you have to first of all to show that all the first order operations can be simulated by solvability problems. So how can we express negation? This is maybe the only interesting first order operation. Maybe somebody has not my cell phone. Oh. Somebody has not switched off. Sorry. So what have we do for negation? We have to express non-solvability of a linear equation system in terms of solvability. So we have to say a system is not solvable by saying another system is solvable. How can we do this? And here is not very difficult actually. If you remember the method of Gaussian elimination, then you write the matrix plus the solution vector, and then the system is not solvable if and only if you can make some row operations to obtain this row, right? So you have zeros in the row for the coefficient matrix and a 1 in the solution vector. So this means the system is not solvable if there is a combination of rows such that I can get this row. But this is of course again a statement in terms of solvability, and this reduction is very easy. And the same is not only true for fields but also for local rings, so we can also have a more general result in this way. Okay, and now conjunction is very easy because it's somehow built in the problem. We have and is this equation and this equation and so on. So we can only combine two systems into one system to express this. And also if you have parameterized linear equation systems and you want to have that all of them are solvable, then you only combine all of them in one system. Very easy. So what remains is only the nesting of solvability quantifiers. So this is this case I illustrated here. So you would have an outer quantifier and such an inner quantifier, which you want to combine into one. So it looks like this. In this outer system here, we may have some coefficients which are 0 or 1, depending on whether some inner system is solvable or not solvable. Yeah? So this is 0 if this is not solvable, and 1 if this is solvable. And we somehow have to combine this sequential situation into some parallel situation. Okay, so to do this, let's write out the equations in these outer systems a little explicitly. So for every row, so this means for every equation, it looks like this. We sum up over all these coefficients times the corresponding variables, and it should be 1. Okay, so let's start. What I do is only to substitute every coefficient by 1 and introduce new variables. So this is the first thing I do. So somehow the idea is to combine this term in this variable. But of course now this system, this is my new system, this is not equivalent to the old one, because I could only say one of these new variables is 1 and everything else 0, so not equivalent. We require some additional consistency conditions which formalize this idea that this combined should be in this variable. And these are the following consistency conditions. Let's see what they say. They say if one of these new variables is 1, so this is 1, then it should better be the case that also this coefficient ARS is 1. So this was this coefficient. And this makes sense because we have multiplication. And another condition says if when two of these new variables do not agree in their value but have the same index for s, then you see if the s is the same, then of course vs is the same. So the explanation for this difference should be found also in the coefficients. So of course now you can show that this together with this is really equivalent to the old system, but we still have to express these conditions. Of course, they've only shifted the problem. But it turns out that this is possible. If you analyze these consistency conditions more carefully, you will see that they somehow have the form, if some variable in my system is set to 1, then some other system is solvable. Because these coefficients here, they refer to solvability of a linear equation system. So it really has this shape. And this we can formalize. What we only do is to take this system somewhere in my big new system as some independent subsystem and add to every equation this term minus v plus 1. And then you see if v is set to 1, then this would cancel out and we would have the same system as before. And every solution of my big new system would contain a solution of this system. And if v is set to 0, then you would see I could subtract 1 from every equation, and I would have a system which has only zeros here, a homogeneous system which has the trivial solution, so I don't have to care about in my big solution whether this system. Okay, so these are all the steps we have to consider, first order operations and nesting. So let me say what we have proven so far. We have seen that that these solvability quantifiers, at least if you restrict them to fixed finite fields, are very nice as logical operators. They give a very strong normal form in this logic. And we have also seen that at least over a very big class of ring, we can forget about considering them, only consider very simple groups if we think of solvability problems. So, and now, I want to come also, we also have some ideas. So extending this logic with constraint satisfaction problems is one approach, but another approach I want to show you here. What you can also do is to extend logics by permutation group membership problems. What are these problems? So in its basic form, it has the following shape. You have given some permutations, which are bijective functions, and a target permutation, pi, on some set omega. And the question only is, so these bijections will generate a subgroup of the symmetric group on omega, and the question is this target permutation in this group? And it's very interesting that this problem actually is computable in polynomial time, because you might have very few generators but a very huge group. So it's not a good idea to generate the group and then look whether the element is inside. You have to really be much more clever for this. And also the counting version, where you don't only have yes, no also this, but you want to compute the size of this group, is also in polynomial time. And what turns out is that all of the solvability problems you can consider over groups, over rings, also over non-commutative rings, and also the rank, reduces via first order interpretations to these problems, to group membership problems. So why is this? It's not so difficult to see. Consider such a linear equation system, and yeah, let's write the column. Let's denote the columns with CS. Then this system is solvable if and only if the columns generate this solution vector, right? So this is what is the solvability task here. So what we can only do is take every column, multiply it with every possible value for the variable xs, and then consider only the group which is generated by these columns. So it does not matter whether you start in the beginning with a ring or with a group, because at this stage the group is only additive. So it is either are some vectors over this additive group of the ring, or maybe even directly the group. So this is a group, and we only have to check whether B is inside this group. And now you all know Cayley's theorem, which says every group is a permutation group, or more precisely, every group can be embedded into a permutation group. And if you look at this proof of the theorem, then you will see this embedding is very easy to define. So this can be defined in first order logic. So we can every group embed into a symmetric group on this group, and of course then also every group which is which are vectors over this group can be embedded accordingly. So this is the first order reduction, because now we only take this embedding and embed all these generators for this group, and then ask whether B is inside this group. And if you now take fixed point logic plus the counting version, because rank, if you want to substitute rank, you need something numerical, then you can do this with this sharp version. But if you want to only are interested in the solvability things, you can take group membership. And actually it's the other version, CSP. It's not clear whether they are also again related, because CSP is somehow you have constraints. You have to say you satisfy this and you satisfy this. But this group membership is somehow more positive. You say you generate something. So maybe it's one of the open problems is, are CSP and this problem now related? So but I think this was my last slide, and thank you for your attention.
This is a CSP logic. Solvability is exactly questions, can you map it homomorphically to a particular set of relations? Because your solvability over, if I understand you correctly, the coefficients are just 0 and 1, right? So this is a CSP logic. So one question, for example, what's the relationship between the extension with rank and the extension with solvability?
But not all, for example, not all multi-set polymorphisms or relations.
No, this is a particular, I mean, you define CSP relative to a particular set of templates here. Okay? But essentially, once you put solvability, you might as well write there home, because solvability is purely homomorphism question.
Then
it's just a question of how rearranging, what's the proper arity, etc.
You're right. But
there is a difference between the rank, which gave you a number, it was kind of a different kind of logic, and solvability, which I think is exactly what I discussed before, which is that you put the CSP directly into the logic relative to tractable templates.
But then the question is, what about these group membership problems? For example,
I'm asking something more, I think was more fundamental. I want to understand the relation between solvability extension and the rank extension. Rank can express solvability.
Right, but the other way around, it's not known. So the problem is that rank cannot express, or maybe not express solvability over non-fields like rings or groups, maybe. But the other way around, it's also not clear whether if I can solve linear equation systems, whether I can express the rank.
But somehow I think, to me, solvability feels more fundamental. I mean, you took rank because rank was a condition to solve, for solvability. solvability, I think, is the fundamental condition, and it is really a homomorphism
Yeah,
test.
I totally agree. Yeah. But,
I mean, I think you think of this as never mind what the operator is in the logic. This is looking at the solvability operations and seeing which ones are reducible to each other in purely logical terms.
Yeah.
Right, without an order, without the,
Right, right.
and that's what this work is about, seeing the
Yeah.
differences.
But I really think that once you put solvability, you are exactly in the context of photon homomorphism test inside, basically using it as a generalized quantifier, essentially.
Exactly.
Any other questions? Let's thank our speaker again.